Hey guys, kind of here. So today we're going to go on ahead and talk about universal gravitation. Now this ties into what we talked about in terms of circular motion last class, and so we're going to put this all together and we're going to introduce you to Newton's equation to go ahead and explain gravitational attraction. All right, so let's begin with our essential questions for today. Number one, what are the factors that impact gravitational force according to Newton's law of gravitation? We talked about that in terms of the relationship of the equation variables, and we'll look at that today. Number two, what is Newton's gravitational constant and why do the units make sense? So this is really the first time we have a constant, and we'll use this again when we get to electricity next term. But today is your first real introduction to this, and so we have to understand the units that are involved in this and why that makes sense. Number three, how does gravity relate to the tides? And then when we're talking about tides, number four, what is the difference between a spring tide and a neap tide? And then lastly, something that we've already started talking about if you've come to Zoom class, but where does Newtonian physics break down? Okay, it does a pretty good job for things that we typically have here on Earth, but there are spots where Newtonian physics doesn't quite pan out. And what are those? All right. Hopefully, by this point in time, you realize that Newton has done a ton for science and physics in particular, from his three laws that we talked about just earlier up to today when we were introducing you to Newtonian gravity. By themselves, Newton's three laws of motion are a crowning achievement for anyone. But Newton didn't stop there. He took these ideas and applied them to a problem he'd been stumped by, and many scientists had been stumped by for years, and that was the motion of the planets. Now, if you think about how our understanding of us and our relation to the other planets, to our sun, to space have evolved over time, this is a big deal. Copernicus placed the sun at the center of the family of orbiting planets and moons, while German astronomer Kepler proved that the shape of the planetary orbits was elliptical and not circular. But no one had been able to explain the mechanics behind how the motion was occurring. Okay, remember before Copernicus comes in with the heliocentric solar system, it was thought that the Earth was the center of the universe. And this was not challenged for a long time. But okay, so we have Copernicus, he puts the sun at the center. Kepler comes along, changes the shapes of the orbits so they're not doing what we call these little ellipticals, these circles on circles to go ahead and travel around. But then Newton comes along, and according to story, Newton saw an apple fall to the ground and was seized by inspiration. He started thinking, whoa, could a falling apple be related to a revolving planet or a moon? And he believed it was. So his idea of gravitation could then be expanded to not only apply to things falling here on Earth, but to things falling in space. And it was an interesting concept because people didn't really think about things falling in space. They thought about them as being orbiting and that that was somehow different. But Newton was able to see that this idea of gravitational attraction could explain that a forward moving object would arc and that that would produce an orbit. This was a big leap. When he connects the motions of cannonballs and falling fruit from trees to the movements of the planets, linking the heavens and earth, this is really one of the first times that we start realizing that the laws of physics on our planet may be the laws of the universe. And his law of gravitation remains one of the most powerful ideas of physics, explaining much of the physical behavior that we see on a regular basis. Now, Newton argued that all bodies are attracted to each other through the force of gravity, and that the strength of that force drops off with a distance squared. And this is going to be a big thing too. I introduced this to you when we first started talking about gravity, but this idea of what we call an don't like yellow, let's switch colors. What we call an inverse, should be an N, let's try that again. Inverse square law. And what this is inverse square 1 over your variable. In this case, we're going to look mostly at distance. So d squared. You can use r squared, something like this. But this is going to produce a parabolic drop. Okay, so the closer together the objects are, the stronger the attraction. But as they get farther and farther apart, it way down. It decreases fairly rapidly. And remember, if we're thinking about our four fundamental forces of the universe, right? We had the strong nuclear, we had the weak nuclear, we had electromagnetic, and then lastly, we had gravitational. So remember that this is the weakest. If we go 1, 2, 3, 4, this is the weakest of the four fundamental forces. And it decreases with what we call an inverse square. So this is a pretty big deal, this stuff that Newton comes up with here. And he really was the first person to kind of start thinking about it in this fashion. It was his thought process that proved this, and an apple falling to the ground must be under the influence of a force. This relates back to F equals ma, so Newton's second law. That force is gravity in this case, which causes the apple to accelerate towards the Earth's center. Newton reasoned that the moon might be under the influence of the Earth's gravity as well, but then he had to explain why the moon didn't fall to the Earth. Unlike the falling apple, it moved parallel to the Earth's surface. And so that forward motion, inertia, right, Newton's first law, kept it in motion forward. And the force, the centripetal force that we talked about, is going to pull it towards the Earth, which is bending its arc. But if it was going fast enough and far enough out, that arc would continue in that circular or elliptical orbit around the other planet. So number 3, what if he wondered the moon moved about the Earth in the same way a stone whirled around the end of a string? Think about at the time stories like David and Goliath. You have your sling that's going to go ahead and propel the rock, and it twirls above the head in a circle before being released. Now, when released, that stone takes a tangential motion, straight line away from the point where it was released. If gravity were to stop, Newton started thinking about whether or not this would be true for the moon, or whether the Earth would do this from the sun, etc. So this is an important concept to keep in mind. When we go ahead and start looking at heavenly bodies, they really don't behave any differently than this and would continue on that tangential path. Now, if the holder of that string didn't let go, though, that stone would continue to travel in a circular path, that periodic motion that we talked about before, just like the face of a clock. In one instant, the stone would be at 12 o'clock, the next it would be at 3 o'clock, and the force is required to keep pulling that inward. This force, in this case, would then be gravity, like the string in our previous example. So then Newton reasoned that the moon orbiting the Earth was the same as the stone whirling about on its string. The Earth behaved as the holder of the string, so if you were to spin something above your head, and this exerted that inward directed force on the moon. The force was balanced by the moon's inertia, which tried to keep it moving forward in a straight line tangential to the circular path. So finally, Newton extended his line of reasoning to any of the planets revolving around the sun. Each planet has inertial motion balanced by gravitational attraction coming from the center of the sun. It was this stunning insight that led him to develop his universal law of gravitation. So according to this law, any two objects in the universe are attracted to any other two objects, any other object in the universe. And it depends on two things. One, the masses of the objects, and two, the distance between them. So the more massive the objects, the bigger the gravitational attraction. The bigger the distance between those two objects, the weaker the attraction. And that's that inverse square that we talked about earlier. So if we take a look here, you'll notice r squared on the bottom. That's that inverse square. Okay. And then when we take a look at the top, this is mass, which is going to be in kilograms, and distance, which is going to be in meters. Okay. And we can relate this very much to the gravitational force. So I'm going to go ahead and write this as F grav, or force gravitational. This is the new piece that we're going to be looking at right here. This piece is the gravitational constant. And I realize that you haven't dealt with one of these really before, but this ends up being important. And we're going to go ahead and take a look at this again when we get into electricity and magnetism. Okay, so G represents the universal gravitational constant, and that plays a big role when we go ahead and take a look at this equation. Okay, so the constant proportionality is going to be something that ties the force to these terms that Newton came up with. And the exact value of this number wasn't determined until after Newton's death by Henry Cavendish. You may have heard of Cavendish laboratories, that type of thing. And those are what it's named after. Now look at the units. This ends up being important. So when we take a look at these units, notice that we have Newton. Okay, there's a unit. We have m squared for distance, and we have kilograms squared. Now this should make some sense because again, we're looking at kilograms, and meters squared. So when we start trying to calculate this, if we're going to end up with a force, which we should know the unit is a Newton, we have to get rid of the kilograms and meters. And so our gravitational constant helps us to do this. So meter squared is on top, which is going to cancel with meter squared on bottom. Kilogram squared is on bottom, which is going to cancel out with kilograms squared on top, leaving us simply with newtons, which is the measure for a force. So experimentally, this was determined, and it's 6.67 times 10 to the negative 11th. All right. You'll never really need to memorize that for me, but it's a good number to know. So the gravitational constant of G, 6.67 times 10 to the negative 11th Newton meter squared per kilograms squared. Okay, so let's do a practice problem so you can try using it and we'll see how you do. So in this one right here, determine the force of gravitational attraction between the Earth, mass of 5.98 times 10 to the 24th kilograms, and a 70 kilogram physics student if the student is standing at sea level and the distance of 6.38 times 10 to the 6 meters from the Earth's center. Now, if you think about it and how we do center of mass and our free body diagrams, this should make sense. So we're using it based on distance to the center of the Earth, where the mass is concentrated. You will need to go ahead and include the gravitational equation, F equals G, which is the gravitational constant. I've given it to you there on the right. M1 is the mass of the first object. M2, the mass of the second object. It doesn't really matter which one you assign to be 1 or 2. And then R squared, is the distance between the two objects. Okay, so take a minute, pause the video, and go ahead and try and calculate this out. Okay, welcome back. What did you come up with? So the answer I came up with is 686 newtons. So let's go ahead and take a minute to go ahead and try and work with this. Let's try setting it up first. So we're going to use our equation from below. We're solving for F of grav, and we're going to do so using the gravitational constant, which in this case is 6.67 times 10 to the negative 11th. Always try and include your units because units can play a huge role. We go ahead and times that by M1, which M1, 5.98 times 10 to the 24th kilograms, and 70 kilograms. And then the distance between them, 6.38 times 10 to the 6th meters, all squared. Now, this is one place where you're going to have to really know your particular calculator. In order to enter this properly, to get the correct answer, you're going to have to do order of operations. So you're going to have to do 5.98 times 10 to the 24th first, then times that by 70. Then you're going to divide that, but you have to do 6.38 times 10 to the 6th first before you square it, and then you go ahead and do the division. Okay, but again, notice here that we're going to get our units to cancel. So we've got a kilogram here, we've got a kilogram here, that's kilogram squared. We've got meters and squared, so these are going to go ahead and cancel, leaving us with newtons, and that ends up being 686 newtons, according to my calculations. Okay. All right, so let's try another one. Give you a chance to try this now that you've kind of seen one set up. All right, determine the force of gravitational attraction between the Earth and a 70 kilogram student if the student is in an airplane at 40,000 feet above the Earth's surface. This would place the student at a distance of 6.39 times 10 to the 6 meters from Earth's center. Now, this is the same setup. We're going to use the same equation and the same gravitational constant. Okay, so go ahead and set this up. See what you can go ahead and do. If you need that equation again, F equals the gravitational constant m1 m2 over r squared. All right, so pause the video here, give that a try, and then we'll go ahead and take a look at your answer. All right, so what did you get? Okay, this time I got 684 newtons. Now you'll notice in this case that it got lower. Why did it get lower? That's right, because we've moved farther away from the other object, and as distance increases, the strength of the attraction decreases. All right, so let's go ahead and do another one. That one was very similar to the previous one, so hopefully you go through those steps and you understand it. We can go ahead and write it out here. F gravitation is equal to the gravitational constant, 6.67 times 10 to the negative 11th. Ooh, if I can remember the newtons, Newton meters squared per kilogram squared times 5.98 times 10 to the 24th kilograms, 70 kilograms, all over our distance, 6.39 times 10 to the 6th meters squared. Okay. All right, if you need more help, please don't hesitate to reach out and we can go ahead and go over this together in more detail. All right, one more. Let's set this up. Determine the force of gravitational attraction between two 70 kilogram physics students if they're standing 1 meter apart. Now, I told you, and when we first introduced this, you can use that great pickup line where you walk down the hall, see that guy or girl you're interested in. I know you're attracted to me. It's the laws of physics, right? Well, this is why. It's gravitation. So go ahead and do the math here. Again, remember, we're going to go ahead and use the same equation. F of gravity equals gravitational constant m1 m2 over r squared. Okay, so pause the video here, give this one a try, and then we'll take a look. Okay, welcome back. What'd you guys figure out? Okay. I got 3.27 times 10 to the negative 7th newtons. That's pretty small. I didn't say how strong the attraction was. I just said that there was an attraction there. So let's go ahead and take a look at how we could set this up. F grav is equal to gravitational constant, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared times m1. Okay, that is 70 kilograms times m2, 70 kilograms, all over the distance, 1 meter squared. So this one is pretty easy. I'll actually go ahead and write it out because it won't take quite as much space as if I were to do it on the previous ones. So F of grav equals 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. 70 times 70 is 400,900 kilograms squared. 1 is still 1 squared, and that's meters squared. We cancel meters, cancel kilograms. So then we times that by 6.67 times 10 to the negative 11th. And look at that. 1, 2, 3, 4, 5, 6, 7. 3.27 times 10 to the negative 7th. Very good. And we're left with newtons, so we can just pull that down. Newtons. All right. Excellent work, guys. Okay. So one more. I'm just going to give you the answer here. I think you're getting the hang of this. So determine the force of gravitational attraction between a 70 kilogram physics student and the moon. 7.34 times 10 to the 22nd kilograms if the student is standing on the surface of the moon at 1.71 times 10 to the 6th meters. The setup is exactly the same as what we've done. The equation is the same. Force of gravity equal to the gravitational constant, m1, m2 over r squared. Okay, pause the video here and go ahead and try it out. Okay, welcome back. What did you end up with? I ended up with 117 newtons. So definitely more, but nowhere compared to the Earth, but definitely greater than what we saw between two people. Okay. All right. So what have we learned from these practice problems? Well, hopefully you've learned that mass has an impact on the outcome. Okay. The bigger the masses are, either one of them, the bigger the force of attraction. On the flip side, however, distance also plays a role. And so the bigger the distance, the smaller the attraction. And that's an inverse square. So that gives us that shape that we looked at before when we go ahead and start looking at this. Okay, there's their parabola. Okay, so this is an inverse square, but this is a direct relationship. This is why it doesn't matter which one gets labeled as M1 and M2, because they both equally impact the attraction force that we see in gravitation. Okay. So this is kind of what it looks like. If you take a look at the forces, notice that we have our A centripetal, which is the A of the moon, the acceleration that it experiences due to this gravitational attraction. And you'll notice that the V coming off of it is the tangential or linear velocity. And that, if you somehow are able to get rid of the gravitational attraction, would continue on in a straight line at the same speed as it was at the point where the gravitation stopped. Now, there's a really cool example of where this is discovered, or this was utilized, I should say, and that was when we discovered Neptune. In the early 19th century, astronomers noticed that Uranus did not follow a simple orbit, but acted as though there was another body disturbing it. Various predictions were made based on Newton's law, and in 1846, the new planet Neptune was discovered close to the expected position. So we use the math as a predictive tool to go ahead and determine the existence of a planet that had yet been to be discovered. This is pretty amazing. Now, Neptune has a mass about 17 times that of Earth and is one of the gas giants with a thick, dense atmosphere, hydrogen, helium, ammonia, and methane smothering a tiny little solid core. The blue color of Neptune's clouds are due to the methane, and it has the strongest winds in the solar system, reaching as much as 2,500 kilometers an hour. So really pushing. All right, the last thing I wanted to cover today is the impact of gravity on tides. Now, Newton describes the formation of ocean tides on the Earth in his book Principia Mathematica. Tides occur because the moon pulls differently on oceans on the near and far sides of the Earth compared with the solid Earth itself. This differential gravitational pull on opposite sides of the Earth causes the surface water to bulge both towards and away from the moon, leading to tides that rise and fall every 12 hours. Although the more massive sun exerts a stronger gravitational force on the Earth than the moon has a stronger tidal effect because of how close it is to the Earth. Now, there are two different types of tides that I'd like to go ahead and talk about, and those are spring tides and neap tides. And this depends on where the sun, earth, moon system is set up. If it is at a right angle, like you see here, so there's the plane of the sun and the earth, and there's the plane of the earth and the moon, this is what we call a neap tide. Okay? When you have a spring tide, you'll notice that they're all straight together in a line. So this is important when we start thinking about it. In a neap tide, because the gravity isn't aligned, you end up with the weakest tidal results. And when you have a spring tide, you have the greatest tidal variance. So spring tides produce incredibly high tides, but also incredibly low tides. Whereas in neap tides, you have a much smaller differential between the two. So I want to give you an example of this. One is the Bay of Nova Scotia. And the Bay of Nova Scotia is an interesting example because it has one of the greatest tidal differences known on the planet. Okay. So the Bay of Fundy is a bay in the Atlantic coast of North America on the northeast end of the Gulf of Maine between the Canadian provinces of New Brunswick and Nova Scotia, with a small portion touching the U.S. state of Maine. The Bay of Fundy is known for its high tidal range, and the bay is contested for having the highest vertical tidal range in the world. There is also a place in Alaska that's in the running for the highest tidal range as well, but I'll show you this quick video. It's old and it's low quality, but it gets the idea across. All right, enjoy.
Here in the Bay of Fundy, Nova Scotia, the tide is out. At this time of day, boats rest on a bed of rock and mud. Through this channel, the twice-a-day change of tide may raise and lower the water level as much as 16 meters. What causes the tides? A bulge of water is created by the gravitational pull of the moon, which is stronger on one side of our planet. Another watery bulge forms on the other side of the Earth. This bulge is caused by the rotation of the Earth-Moon system. When a landmass lines up with this Earth-Moon system, the water around that landmass is at high tide. In contrast, when the landmass is at right angles to the Earth-Moon system, the water around it is at low tide. Thus, every landmass is exposed to two high tides and low tides every 24 hours. By means of time-lapse photography, we will watch high tide return to the Bay of Fundy.
Now, I hope you guys were watching the kind of wall there and back. I think it gives you a good perspective when you start seeing just how much water is coming in there. You're looking at approximately a 50-foot swell in terms of the tidal difference, so it's pretty impressive. Okay, so over the years, scientists in just about every discipline have tested Newton's laws and found them being amazingly predictive and reliable. However, there are two instances where Newtonian physics begin to break down. The first is objects traveling at or near the speed of light. This deals with what we call time dilation. And they've actually done some tests here on Earth with supersonic flight, where they have two perfectly synced radioactive clocks. One of them goes ahead and flies in the supersonic jet around the planet. The other one stays put. And when they land the jet, the two are no longer synced. So time is experienced differently depending on the speed the object is traveling. And so that impacts Newtonian physics. Two, the second problem comes when Newton's laws are applied to very small objects, such as atoms or subatomic particles that fall into the realm of quantum mechanics. Quantum mechanics is a weird, strange thing. And if you have questions, I'd be happy to try and answer them, but I'm not going to pretend that I know enough to really be authoritative in terms of quantum mechanics. I feel like I have a decent, pretty good understanding of relativity, but quantum mechanics still baffles me, understanding the different particles of the quantum zoo, etc. But scientists still do not stand still. This is one of the best things about science, is that if you remember CONPTT, testable, tentative, it's constantly changing as we get new data, new technology. And so as we go ahead and continue to go ahead and expand our understanding of the universe around us, we will look for ways to test it. When Einstein first introduced his theories of relativity, they weren't testable. So it was what we called theoretical physics. But since that time, we were able to go ahead and do tests like Gravity Probe B to go ahead and get the data in terms of the dragging of space time itself, which allows us to go ahead and validate the work or predictions of Einstein. And so it's pretty impressive that we have these tools, but even that, keeping all that in mind, what we learned from Newton is super powerful because for everyday types of things, you can see those exemptions are not things we deal with on a regular basis. They do an incredible job. Okay. And so for most of what we do, from everything from our orbits to things dropping on our planet, Newtonian gravitation does an incredibly good job. In fact, it was good enough to actually find Neptune. And so, yes, there are cases where super massive things or super fast things or super tiny things don't seem to match what we see in Newtonian gravity. Mercury's orbit is actually distorted due to relativity and the mass of the sun being so close to Mercury. But for the most part, we can neglect those types of things for what we deal with on Earth. All right, guys, take care of yourselves. I hope you had a good day. Take care of yourselves. Stay safe, stay healthy, and we'll talk to you soon. So long, guys.